Okay, we are in average value of a function. This is another application of integration. So they mention that they start off that it's easy to calculate the average value of finitely many numbers. So to take the average of a set of numbers, you add the numbers up and divide by the total. Okay, so like for instance, if you had numbers 7, 4, and 9. Hold on. Let's do 7, 4, and 10. Okay. What's the average value of these three numbers? 7 plus 4 plus 10. What's the average value? 7, right? Okay, and how did you get that, Mario? Okay, you took 7 plus 4 plus 10 and divided by 3. And you got 21 divided by 3, which is 7. That's how you get the average value. Okay, that's how you get the average value. So that's fine. That's fine. So now when we, go to the book here, okay, if we want to find an average for a number of values, y sub 1, y sub 2, up to y sub n values, we add them and divide by n. And these values come from some function. But how do we compute the average temperature? For instance, how many have heard of the average temperature? What's today's average temperature? You see it on the news, like in the morning. How many have, or in the evening, how many have seen that? Like when you watch the news, local news. Okay, Ange knows that. And how do they get that average temperature? Okay, how do they get an accurate reading? Well, you could find the average temperature by sampling really infinitely many temperature readings. Okay, you could do that. How would that work? Well, let's take a look here at figure 1. Figure 1, there's a picture of an average temperature function. It's in blue. And gee, the axis there, the t-axis goes from 0 to 24. Why would that be? Why would the axis go from 0 to 24 on the t-axis? That's right, Taj. That's the number of hours in a day. There are 24 hours in a day. And so there's the temperature function. Now, the temperature function seems to be lowest at t equals 6. T equals 6 would be what time? What time of day? Six a.m. That's right, Taj. 6 a.m. Okay. And so, temperature is pretty cold at 6 in the morning. I used to have a newspaper route, and I would deliver papers in the morning. And 6 a.m., man, it's pretty cold at that time. But now look what's happening. At 12, t equals 12 at noon, the temperature's going up. Why would that be? And then it's highest at 18. 18 would be what, 6 p.m., right? T equals 18 to 6 p.m. Why would the temperature be highest at those times? Well, getting higher and highest at 6 p.m. What's causing the temperature to increase? The sun. Good. That's right, Mario. That's right, David. The sun. So this is a reasonable temperature function. And then in the evening, the temperature falls back down because the sun went down. So we want to try to compute the average value of that function. And what they're doing is, you see they're drawing a red line through the center of the function. What's the height of that red line? If you had to estimate the height of that red line there in figure 1, what would you estimate the average temperature to be? Okay, Mario's saying about 4.9, and I agree. And you can see visually, I mean, you know, the average temperature, you can visually, if you have this daily, you have this temperature function, it's a continuous blue function there. And using your intuition, you would estimate the average temperature would be about 4.9 degrees Celsius based on the data from that function. Okay, so the question is, can we come up with an integral that will give us this average temperature? And the answer is yes. Okay, so are there any questions so far? Okay, okay, very good. Well, so what we can do is we can define these temperature readings by function values. Now, of course, we would need some function to model the temperature throughout the day. But let's say we have that function. You know, in science, business, there are functions that model many, many, many things. Okay. So if we have these function values and we wanted to find the average, we would just take the average. But if we take more and more samples of the temperature, okay, then you know, let's think about what the subintervals are. So they're saying here, and I'll move this up a little bit, that we can take the temperature function and divide the interval from A to B into these subintervals, just like section 5.9, you had subintervals. And we can, if we sample more and more temperature readings, we would have to take the window of time from 0 to 24 hours and break it up into smaller and smaller subintervals. Each subinterval, we would take a temperature reading. So delta X would be equal to B minus A divided by N. That's just like section 5.9. Okay, you have a beginning limit and an end limit. What's the length of your subinterval? You know, you're applying the trapezoidal rule or midpoint rule. The delta X is B minus A divided by 9. So look at what we can do here. So this is the average value of our function based on N estimates, the highlighted box. But we can replace N. We can replace N with B minus A divided by delta X. Because if delta X is B minus A over N, I can actually go to the whiteboard just to show this. It's not hard. If delta X equals B minus A divided by N, then we can multiply both sides by, hold on here, by N. So N times delta X would equal, I mean, these N's would drop out, right? Simplify out. N times delta X would equal B minus A. And so N this is section 6.5, Sandia. Yeah. N is equal to B minus A over delta X. You're welcome. So I'm going to take this value of N, let's see here, which is B minus A divided by delta X, and I'm going to substitute in then for my average value of my function values. I'm going to replace N with B minus A over delta X. But then delta X, you can multiply on the top and the bottom, and delta X will simplify out on the bottom. And so you're left with the average value of the function being equal to 1 minus B over A times all the function values, each well, 1 over b minus a times the sum of the function values multiplied by delta x. And then you can write that as a Riemann sum. Are there any questions on what you're seeing in the highlighted box there? Okay, well now what are we going to do with n? What are we going to do with n? If we want a more accurate estimate of the average value of the function, we have to take more and more subintervals. That means we have to let n increase. And what are we going to let n? We're going to let n increase. We let n increase, but what do we let n go to then? To find the true infinity. That's right, Ange. So by letting n go to infinity, we will get then a formula for the average value, the actual average value of a function. And there's the formula. Now this is section 6.5. It's not on your second exam. It'll be on your third exam, right? But there you go. Now you have a formula for the average value of a function. The average value of a function is equal to 1 over b minus a times the integral from a to b of f of x dx. Are there any questions on that? Okay, well then let's go to an example here. Let me see. Did I upload? Okay, hold on, class. I got to upload the document here. One moment. This will just take a moment. Forgot to do that. That's okay. Let's do it now. Okay, one moment. Just give me a moment. We'll get it. Okay, it's uploading now. Okay, excellent. Excellent. Okay, so let's do a problem here. Let me give you a moment to copy this example down. Okay, there was a question. One moment, let me see. Sandia, I will show you the formula. We will be using the formula. Do not worry. When we go over the solution, you will see the formula again. Not a problem. So what we're going to do, we have this function. And I'd like to graph this function in Desmos. F of x equals 1 plus x squared. I want to graph it in Desmos over the interval from -1 to 2. Okay, so we'll move to Desmos in just a moment here. This is a quadratic function, Sandia. Indeed it is. And definitely we want to have a look at what it looks like. So, all right, if everybody's good, I'll move to Desmos here. Okay, so I typed in 1 plus x squared, but the window I want is from -1 to 2. So I'm going to go to the wrench here, and my x-axis, I'll just make it from -1 to 2. And then the y-axis, let's see, maybe I'll make it go from 0 to maybe 8, something like that. Not 81, 8. Okay. And let me see. Got to be a little careful here. Now wait, that didn't do. Let me go back to the wrench. I want -1 on the money. And I want 2 on the money. Let me just see here. One moment, class. I guess when I move around, it changes things a little bit. Say maybe 6. Okay. So there's a graph of the function over the interval from -1 to 2. And what would you estimate the average value of the function is? Do you think the average value is, well, if you had to estimate it, think about all the y values of the function from x equals -1 to 2 and adding up all the y values. Okay. What do you think a reasonable average might be for this function? A reasonable average value might be. Okay, Tosh says somewhere around 3. Nathaniel says between 3 and 4. Ange is at 2.3. So we're getting different values. Let me ask you this. What we're going to do, we're going to find the average value, and then we're going to go back to this picture. So think about that. Let's go back to the example here. Okay, and let's go to the solution. So I just rewrote, you don't need to recopy this part here. You did recopy that. But now we're going to the solution. So A is going to equal -1, and B is going to equal 2. Okay, and we're looking for the average value of the function. That's called f sub av. Okay, so I can make this a little nicer here. Now, the formula for the average value of a function, the formula, which is there in section 6.5, f sub average equals 1 over b minus a times the integral from a to b of f of x dx. Okay, so a is -1, b is 2, your function is 1 plus x squared dx. And this is just a simple integration problem. A simple integration problem. There's really not a whole lot to it. Okay, and I redrew the picture here. If you were using a TI-8384 calculator, you would let your x go on the window. You let it go from -1 to 2 with maybe a scale of 1, and the y go from -5 to 5 with a scale of 1. That's fine. I mean, you know, but we have a picture in Desmos. The antiderivative of 1 plus x squared is x plus x cubed over 3. And then you substitute in the 2 and the -1. And you work it out, and you're going to get 2. You're going to get 2. So, and you came the closest with 2.3. You came the closest. What we'll do is we'll go back to the picture and draw in that average, the average of 2 on top of the Desmos, on top of our graph, and that'll help. It's always nice to get a graphical idea. Okay, and I'll go back to Desmos then when I'll give you another moment to copy this. Are there any questions at all? That's an equals there, right? Okay, if you're good, let's go to Desmos, back to Desmos, and look at that picture. Okay, and I'm going to put in the line y equals 2. Okay, so you see there, there's y equals 2. And based on this point here, the 1, 2 point, in terms of like the y values, are there more y values below 2 or above 2 for this graph? Are there more y values below 2? Like look at the red function, the y equals 1 plus x squared. That's the red function. If you think about like y values and all the, like, you know, think of the x values, but then the corresponding y values. Are there more y values on the, you know, more y values on the function that are below 2 or above 2? Okay, so let me ask you this. Hold on. So for coordinates on the function, hold that thought, Tosh. For coordinates on the function, okay, that have y values smaller than 2. What's like the range on the x? For what x values is y less than 2? For what x values are the y coordinates on the function less than 2? Give me a range. Okay, x equals -1 to 1. That's right, Tosh. Now, give me the range for the x values where y is above 2. From 1 to 2. That's right. Okay, so, you know, more x values have y coordinates that are below 2 than the number of x values that have y coordinates above 2. So what I'm trying to say is more of the graph, if you look at this, the way this graph is graphed between x equals -1 to 2, more of the graph lies below 2 than above 2, right? All right, more of the graph lies below 2 than above 2. Yet the average is 2. Can you intuitively tell me why that would be? Why wouldn't the average be below 2? More of the graph, you know, more of the graph is below 2 than is above 2, but the average is 2. What's causing that average to be pulled to 2? Why would the average be like 1.5? Well, think about the y values. What's happening to this function as you move further and further towards x equals 2? We see the functions increasing. You might have hit upon something there, though. Hold that thought, Mario. As x increases, the function increases, right? I mean, let's focus on, like, I want to say this the right way. If we look like after x equals 0, the function's increasing. Is the rate of well, I'm going to say this right. Is the increasing getting greater or less as you go to the right? What's happening to the function? Is it like, is the rate of increase more, or is the rate of increase going up or down as we move to the right? It's going up. That's right, Sandia. So the rate of increase is going up. So that's going to pull your average up. In other words, for the y values after that coordinate 1, 2, if you look at the y values on like this portion of the graph here, if you look at the y values there, they're getting greater and greater and greater. And so that's going to influence the average, because here, like the y values here, they're increasing, but not at as fast of rate. But the y values here, they're increasing, and they're increasing at a faster rate. So that moves the average up. You see what I'm saying? It moves the average up. Does that make sense? Good, good. So it's like if you think about like baseball salaries. Okay, you have a lot of players, and I'm not an expert on baseball, but let's say that you have a lot of players that make, maybe, you know, I think about the movie Moneyball. You know, you have a lot of players that make maybe $250,000 a year, maybe $500,000 a year, professional players to play baseball. But then you have some of the players that make 10 million a year. Well, that moves the average up. Okay, when you have like those bigger values will skew the average, so to speak. It'll make the average go up. Does that help? Is that a good analogy? What do you think? I'm just trying to give you, all right, Javier's seeing that, and Anne's seeing that, and Mario, excellent. Trying to give you an intuitive idea of what's going on here. I don't want you just to compute the average value of a function and say there's the average. I want you to understand why it's in a sense, why the average makes sense. All right, are there any questions on that? Y equals 2 is from the answer. If I go back to the solution, so here is the answer right here. So the average in this case, so the average value, you know, we started from the formula here and worked out the integration and arrived at the average value equals 2. Mario, is that, so you're comfortable with that? Or, okay, good. Are there any other questions? Okay, I'm going to stop the recording. I mean, really, that's what section 6.5 is about. And average value of a function is used, for instance, if you model the temperature values throughout the day. You can, if you have a function to do that, you can find the average temperature. If you like velocity of blood, you could find the average velocity of blood, for instance. There's all kinds of applications. The average velocity of a car, you know, so long as you have a function that models the phenomena going on, you can get the average value. And it's really quite, how many think this is kind of amazing, that it's so easy to get the average value of a function? How many think that's kind of an amazing idea? Okay, Anne's just liking it. Joseph, great. And Taj, excellent. I haven't heard from Joseph in a little while. Good to see you, Joseph. So, you know, I kind of trust everybody who's here. I hope they're here, you know. And I hope you're having some fun too learning. Okay, I'm going to stop the recording.